this one. Good evening, everyone. This is Roxanne Truen with the Michigan State University Science Festival, and we're with our last talk of Statewide Astronomy Night tonight. And I will mention before we get started, if you have questions for our speaker tonight, you can type them into the Q&A function on the Zoom webinar. And if you're on our Facebook Live feed, you can type questions into the comment section. Excuse me. And now I'm going to turn it over to Mark Reed, who's the planetarium manager of the Kalamazoo Valley Planetarium.
Good evening. As the planetarium manager of the Kalamazoo Valley Museum Planetarium, I am pleased that we are able to participate in this year's Statewide Astronomy Night. It's part of Michigan State University's Science Festival. As part of tonight's lineup, we've been able to make arrangements with Dr. Axel Mellinger of Central Michigan University. Dr. Mellinger is a professor within the physics department who amongst has passions and is known for his photography of the Milky Way galaxy. His work appears in numerous astronomy publications, planetarium presentations, and on the Astronomy Picture of the Day. Please give a warm welcome to Dr. Mellinger for his talk, Photographing the Milky Way, Giant Panoramas and Time-Lapse Videos. I think you'll enjoy this talk.
All right, thank you very much, Mark, for your introduction. Let me just start sharing my screen. Here we go. Okay, so my presentation tonight is going to be a little personal story of my journey into astrophotography. So I'll talk a bit about the film age or the dark ages of astrophotography and how I got to shoot my very first Milky Way panorama. I'll then talk a bit about the newer techniques using CCD and CMOS cameras. I'll also talk a bit about light pollution, which is one of the main problems that astrophotographers face today. I'll talk about how I created my second all-sky Milky Way panorama. And then in the last part of my talk, I'll talk about my more recent endeavors into time-lapse astrophotography. So, astrophotography in the 20th century looked pretty much like this. You had a camera, you loaded it with film, then once the film was full, you took it out of the camera and you either dropped it off somewhere or you dumped it into some chemicals yourself. You ended up with a negative or maybe with a positive slide, and then that had to go into an enlarger and you ended up with a paper print. So my very beginnings in the early 1980s was with a telescope similar to this one, a 60mm refractor, had an equatorial mount, and it was hand guided. And when I say hand guided, I really mean I had to turn those flexible shafts slowly, keeping a guide star centered on the crosshairs in the eyepiece. I scavenged an old, I think 1950s era camera from my parents, loaded it up with some film, and this was my very first astrophoto. So if you take a look, you might recognize here it's Vega, constellation of Lyra, and then here is Deneb in Cygnus. This is right in the Milky Way, although from the light polluted backyard of my parents' home near Munich, Germany, you don't really see that much of the Milky Way. I was pretty thrilled, although later on when I inspected the picture, well, there's some room for improvement. For example, astrophotographers will probably recognize when some parts of the image have pretty pinpoint stars and other parts show little trails. That's a telltale sign of field rotation, meaning I did a lousy job on polar aligning the mount. Anyway, I was hooked on astrophotography, and a couple of years later, I had a chance to travel to the southern Austrian Alps, and that was my first really deep Milky Way photo, black and white, Kodak Technical Pan 2415 film. Now, let's go forward another decade, or we're now in the mid-1990s. And at that time, scanners became available. So you could scan your negative or slide and then process it on a computer. What really made this possible were advances in computer technology. So let's just do a little bit of math. A reasonably high resolution image has maybe 3000 by 2000 pixels. So that's 6 million pixels. You need at least 3 bytes per pixel. So that's about 80 million bytes, 80 megabytes. Now, the typical RAM of a 1996 PC was around 60 megabytes. So that meant with investing a little extra money, you could upgrade it to 24 or 32 megabytes, and that put image processing within reach. And of course, with digital image processing, you had all the tools available to brighten or darken your image, remove vignetting, remove distortions, and also assemble mosaics. I'll come to that shortly. I was doing a postdoc at UC Berkeley at the time, and I joined a few astronomy clubs in the San Francisco Bay Area. And one of them does an annual trip to the Eastern High Sierra. The University of California runs a research station there at 12,500 feet. And it was there that I did my first digitally processed Milky Way picture. Okay? So just to show you a few of the features here, the bright star, that's Antares and Scorpius. The nebula here close to the center of the picture, that's the Lagoon Nebula, M8. The dark nebula here, that is the Pipe Nebula. See the pipe here with the smoke coming out. Then I moved back to Germany for another postdoc. And from Germany, if you fly straight south for about 12 hours, you end up in Southern Africa. And I had some friends there from my research connections. And so in early 1998, I had a chance to travel to South Africa. And yeah, I met those guys. And about 120 miles north of Cape Town, there's an observatory run by a group of amateur astronomers. And I've visited that observatory since many, many times. And here's a view of the southern sky. So this is a star trail picture where I just did I think about an hour-long exposure. You will notice there is no bright star near the center. There's no Polaris in the southern hemisphere. Those two fuzzy objects near the bottom, those are the two Magellanic Clouds, our nearest neighboring galaxies. And here's a picture of a very interesting part of the Milky Way. So right in the center, we have the Southern Cross with Alpha and Beta Centauri off to the left. Next to the Southern Cross is a dark cloud called the Coalsack. And over to the right, we have a bunch of star clusters and very prominently the Eta Carina Nebula. So I started taking a few pictures of the southern Milky Way on that trip and then put them together to a mosaic. Why do you want to do that? Well, one advantage is you can cover a larger field of view than your camera would otherwise allow. Now, of course, you could also use a wide angle lens or a wider angle lens, but in doing so, you lose resolution. You no longer resolve as much detail. So instead, if you'd stick with a longer focal length, shoot multiple segments, and then combine them to a mosaic, you end up with large, very high resolution images, which are ideal, for example, for projecting in a planetarium. Another advantage is, especially when you think of the later CCD cameras, which initially had pretty small chips, you could get by with using smaller, less expensive cameras. Now, when you combine several frames into a mosaic, you unfortunately run into a problem that has to do with the geometry of mapping or imaging the celestial sphere onto a flat surface, either your film or your electronic sensor. So let's imagine we have 3 stars in the sky, and they are both separated by equal angles. Where do they end up on the sensor? So we take the star here in the middle, draw a line straight through the camera lens, and where it intersects that plane that's labeled film, that's where the star will end up on the film. Let's do this for the next star. That's going to end up here. And let's do that for the 3rd star, and that's going to end up here. And now if you look at the 2 distances, I've labeled them S1 and S2 here between the stars, you see they're not the same, even though in the sky the stars were separated by equal angles. So we have a distortion that increases with the angle between the star and the optical axis, that's the central axis of your image. The good news is, because it's a geometric effect, it can be corrected in software. Now, back in those days, there was very little mosaic software available, so I had to write my own. Now, when a friend of mine saw my first mosaic attempts, he said, you know what? This reminds me of a picture they did back in the 1950s at Lund Observatory in Sweden. And I looked it up, and sure enough, they did an all-sky panorama. That's the one here. Now, back in the 1950s, they didn't have any computer image processing. So what they did was they actually did a painting. They used spray paint and brushes, but based on astronomical photographs. So that was, to my knowledge, the first all-sky panorama. And so I thought, well, what they could do, maybe I can do. So I started piecing my images together. This was back in May 1998. Then by February 1999, see, I already had filled up a pretty good portion of the sky. Another half a year later, most of it done. And then by May 2000, I had indeed covered the entire sky. So just for orientation, in the center, we have the direction towards the center of our galaxy. See the bright star here, that's Antares in Scorpius. Down here, we have the Magellanic Clouds. Orion is over here, tilted a little bit to the side. Here are the belt stars. Below the belt stars is the Orion Nebula. That bright star here is Rigel. Here's Betelgeuse. And that landed me an astronomy picture of the day. And that picture also became quite popular with planetariums around the world. All right, let's move forward to the digital age. So instead of taking a negative and scanning it, the new approach was to use a digital camera with a CCD or a CMOS sensor, and then unleash, again, the full power of computer-aided image processing. Digital photography has a number of advantages. The most important one is that digital sensors have a much higher so-called quantum yield than film. So what this means is that film detects about, at best, 1 out of every 10 light particles, so-called photons. Usually it's more like 3 to 5%. CCD cameras and more recently CMOS cameras, they have quantum yields of the order of 30 to 80%. Okay? So we're talking about a factor of 3 to 8 more. Digital detectors are usually linear. That means the readout that you get is directly proportional to the amount of light that hits the sensor. That's very different for film, which complicates processing. And of course, you have virtually unlimited processing options for digital images. They did, at least initially, have some disadvantages, most notably higher cost than film. And also they have electrical power requirements. Dedicated astro cameras, they usually are they use a cool chip, so you need a few amps at 12 volts out in the field. Now, I want to talk a little bit about light pollution before we move on in the realm of digital photography. So light pollution, as I said, is a major problem for astrophotographers. However, not all light pollution is artificial. So there are some natural sources that brighten up the night sky, most notably so-called air glow. Air glow is fluorescence or phosphorescence light emitted by the upper atmosphere, and it's quite variable both over time and from one point in the sky to another. So if you take a look at this time-lapse loop, you see this greenish color. This greenish color is a manifestation of air glow, and yes, it can look nice, but if you're after photographing the Milky Way, it can actually be a little distracting. There are other sources of light pollution. There is zodiacal light, which is light scattered by dust particles in our own solar system. And even starlight can be scattered by our atmosphere and produce a little bit of background. Let me just ask you, does that video play reasonably smoothly? Because I think I did not use the video mode of sharing my screen.
Yeah, so the video looks good.
Looks good? Okay. All right. Now, onto artificial light pollution. So there are a number of sources. There are the old style incandescent lamps, not used very much anymore for street lighting. Mercury vapor lamps are still quite common. High pressure and low pressure sodium lights are very common, and more recently, light emitting diodes or LEDs. The picture here on the right is a light pollution map of Michigan, and I live in Mount Pleasant right here, and you see that is a moderately light polluted location. Of course, the more urban the area, the more light pollution you have. Light pollution is usually measured or quantified on the so-called Bortle scale, named after an astronomer, John Bortle, who published an article in Sky and Telescope about 20 years ago. It's a scale that ranges from 1, which means best, to 9, which is worst. And just to give you a couple of examples, Bortle class 5, suburban sky, means the Milky Way is very weak or invisible near the horizon. You can still see it, although washed out overhead. Clouds, terrestrial clouds, are noticeably brighter than the sky itself. The naked eye limit of the faintest stars that you can see is around 5.6 to 6.0. Next class, bright suburban sky, Bortle class 6, means that the Milky Way is barely visible in the zenith. The sky within 35 degrees of the horizon glows grayish white. So my location is somewhere in between Bortle class 5 and 6. Now, what can you do against light pollution? Well, there are a few tricks you can apply. So one thing is, if you look at the spectrum of light pollution, depends on what type of street lights you have. HPS, for example, here stands for high pressure sodium lights. So they are reasonably broadband, but they emit most of the light in the yellow, orange to red, not much in the green. LEDs, on the other hand, they are pretty bad offenders. They have a pretty strong blue emission, and blue light is particularly bad because it scatters a lot more strongly than red or yellow light. Depends on which type of LEDs you have. So the LED with the 2400 kelvins, that still has a moderate amount of blue light. The more common daylight LEDs, they have a very, very strong blue contribution. Now, fortunately, some astronomical objects, notably emission nebulas, planetary nebulas, they emit most of their light in just a few very narrow spectral lines. I've painted a few of them here in this picture. For example, we got a very strong emission line called H alpha at a wavelength of 656 nanometers. In case you're not familiar with wavelengths, so the human eye can see light roughly between wavelengths of 400 nanometers to about 700, 750 nanometers. If the light source is faint and you're using your night vision, then it's more limited. Then it's mostly around 450 to about 600 nanometers. What's happening here? Why do these nebulas glow only at certain wavelengths? Well, that has to do with the structure of atoms and quantum physics. So I just want to show you how that bright hydrogen line is produced. So here on the right, we have a very schematic model of a hydrogen atom. So a hydrogen atom consists of a proton in the center, that's the nucleus. And then there is an electron around the nucleus. And that electron can be excited. That means if you add energy, it will be kicked up into a higher orbit. They are labeled 1, 2, 3, 4, 5. And these higher orbits, they are not stable. So if you put an electron there, it will want to jump back to a lower orbit. So for example, if you put an electron into the n equals 3 orbit, it can jump back to either n equals 2 or n equals 1. And if it jumps back to the number 2 orbit, it emits the energy difference as light of that particular wavelength, 656 nanometers. That's the origin of that bright hydrogen alpha line. There are other elements that emit different spectral lines. There are a few very exotic lines emitted by doubly ionized oxygen and ionized sulfur. Those atoms, they're usually ionized and excited by electron impact, and that's a very efficient excitation mechanism, even though these elements are much, much less abundant than hydrogen. And they only exist in space, in the vacuum of space. Here on Earth, those ions would immediately bump into other gas molecules and lose their energy without having a chance to radiate. So these O3 and S2 lines, they're also quite common in nebulas. So now what you can do is you can buy filters, for example, here, one that has a transmission curve just centered around the hydrogen alpha line at 656 nanometers. And this way you cut out all the street lighting and most of the air glow, and you still get 90% of the nebula's light. So here are a few examples. This is a section of the Milky Way in the constellation of Cygnus, the bright star up here, that's Deneb. This was done with a dedicated astro camera. A lot of them are monochrome, they're black and white only. So if you want to have color images, you need to work with different filters and then create a color image by assigning the different images taken through different filters to the red, green, and blue channel. So up here we have a nebula that's called the North America Nebula. I think it's pretty obvious why it has that name. Next to it, the Pelican Nebula. Let's zoom in a little bit. Here's the North America Nebula and the Pelican Nebula again. This was a multi-frame mosaic that I did many years ago with a little CCD camera. Here is another mosaic project I did between 2004 and 2006. This is a Southern Hemisphere object. It's the Gum Nebula. It's a 1 million year old supernova remnant. So again, I took, I think it was 20 something fields through an H alpha filter and pieced them together. This was the astro camera I was using at the time. It had a pretty small chip, only about 9 by 7 millimeters. I also used my very first DSLR, which had a smaller chip size, but that chip isn't cooled and it's not very sensitive at H alpha, but it could record color. So here's that hydrogen alpha black and white image again. Here is the same region of the sky taken through the DSLR, and then I combined the two by substituting my hydrogen alpha image for the red channel. And so yeah, that's a pretty colorful image of the Gum Nebula. Can zoom in a little bit, and that landed me another astronomy picture of the day. Okay, so I had the art of creating mosaics pretty well mastered, and I realized my first Milky Way Panorama picture was showing its age. It didn't quite have the resolution that more modern planetarium projectors could take advantage of. So I started to play with the idea of redoing the Milky Way Panorama, this time, however, as an all-digital image. So I divided the sky into, skip forward a little bit. This time I did it with a lot better planning. So I was actually able to finish that project in less time than my first one. What I did was I divided the sky into 70 fields. See here, those fields all had a fairly generous amount of overlap, which is important if you want to join them without leaving visible seams. This was the camera I was using at the time, an SBIG STL 11000 with a 50mm f1.4 lens that I scavenged from my old Minolta SLR, Note SLR without D. I needed very dark sky sites. And so here are the three sites where I did most of my second Milky Way panorama from. I went again to South Africa to Cedarburg Observatory and a guest farm in the same area. A lot of the northern images were taken from Big Bend National Park in Texas. And then I also took a few from Michigan up north in the Huron National Forest. Just a few pictures from South Africa. Again, this was the guest farm where I did most of my southern skies shots. That friendly little oinker got interested in my equipment, and unfortunately, one day decided that maybe a USB cable sounds like a delicious meal. Well, yep, that was seconds before he started to chew on my USB cable. A few pictures from Big Bend National Park. The rocks here on that side, that's already on the other side of the Rio Grande, that's Mexico. My site at Tilingua Abajo, one of the remote campsites at Big Bend National Park. The star trail picture here shows rising Orion, see the three belt stars, the Orion Nebula. Let's skip that picture. Yeah, this is a younger version of myself back in, I think, 2009. And once I had all the 3,000 images together and assembled them in a panorama, this is what I got. Well, I think you agree this doesn't look quite what you expected. Well, first of all, it's black and white. Okay, this was only the red channel, but more disturbingly, it looks quite patchy. Why is that? Well, light pollution, either artificial light pollution or more commonly natural light pollution. For example, this part here, I remember I took this in the western sky from Big Bend National Park right after sunset, and it wasn't completely dark yet, but I had to do it because otherwise it would have set. So I had this field with a higher background than others. So fortunately, I discovered a reference data set that I could use. Back in the 1970s, the Pioneer 10 and 11 probes on their way to Jupiter, or one of them also flew past Saturn, they had an instrument on board called an imaging photopolarimeter. and that did an all-sky survey en route to Jupiter. And you see the survey here. It was quite low resolution, but that was all that I needed because that data was not contaminated by any terrestrial sources or zodiacal light because it was taken from the outer parts of the solar system. So I used that as a model for my sky background. I had to fudge a little bit because there was a part of the sky where the Pioneer probes could not image because that would have been too close to the sun. Okay, so here we go. That was in summer of or fall of 2009, my second all-sky panorama. A lot more faithful color-wise than my first one. Also a lot higher resolution. Here's a direct comparison of the region around the Southern Cross. The bottom one is my old film-based panorama. The top one is the digital one. And I, at the time, I published an article on the making of it in the publications of the Astronomical Society of the Pacific. CMU picked up the story. NASA used that image to illustrate how the sky is going to look like in about 3.75 billion years from now. You may know that the Andromeda Galaxy and the Milky Way are on a collision course, and so the Andromeda Galaxy pictured here is going to look a lot bigger in 3.75 billion years, and the background, the Milky Way image, that was the one they took from my all-sky panorama. More recently, in 2016, the LIGO collaboration used the image as a backdrop to illustrate the locations of their first two gravitational wave events. Again, the CMU's communications department picked up the story. They did a pretty good work, but then our student newspaper picked up the story as well, and they came up with the headline, "Professor's Research Confirms Einstein's Theory." Well, not so much. Okay, so let me come to the third part of my presentation. So when I finished my second Milky Way panorama, I just moved to Mount Pleasant. I started a family, and so for a while, the Big Dipper gave way to the Big Diaper. So I needed something that I could do more locally and with less equipment without needing to travel to South Africa. And I started looking to time-lapse astrophotography. Why would you want to do time-lapse images of the night sky? Well, there's a lot of motion, actually. The stars move across the sky. Well, actually, it's the Earth's rotation, but nevertheless, they appear to move. You may have sometimes clouds that move through your image. There may be shadows. For example, if you photograph a solar eclipse, you may be able to image shadows. And if you take a time-lapse sequence at a star party, you may see some foreground activity. Now, time-lapse astrophotography poses some special challenges of its own. First of all, of course, it's dark at night. And so you want to use long exposure times, typically 30 seconds or more, and you want to use a reasonably large sensor camera. The larger your sensor, the more light it captures. On the other hand, if you want to play back the images and get a smooth video clip, you need hundreds or even thousands of frames. And of course, that means if you use long exposure times, you run out of nighttime. So you can't really expose much longer than 30 seconds. You also need to think about how to power your camera over an entire night. Nights are cold, so that lowers the battery performance. So you may have to use an external power supply or larger batteries. So here's some of the equipment that I've been using. You want a camera, preferably a DSLR, with a bulb setting where you can expose as long as you wish. And those cameras, you can spend just a couple of $100. You can also spend more than $3,000. You want a super wide angle lens with a reasonably fast f ratio. Now, if you look up the known camera manufacturers, Canon, Nikon, Sony, and look what they offer for ultra wide angle lenses, they usually go for $1,000 to $2,000. Fortunately for astrophotography, there's a lot of features that these lenses have that you don't actually need. You don't need autofocus. You don't need a camera controlled f-stop. And so there's a company called Rokinon, and they market lenses that are pretty much bare bones, like lenses of 30, 40 years ago. They don't have autofocus. So they only have manual focus. You manually set the f-stop. But the advantage is they can be had for a lot less money. This 2.8 14 millimeter lens goes for around $280. You also want a timer. You can buy external timers for about $25 to $60. A lot of DSLRs have built-in interval timers. If they don't, especially some of the earlier Canon models, they don't, but there is a firmware extension called Magic Lantern that you can install on the camera, and that gives you that intervalometer feature. So this way you can tell that your camera take a 25-second exposure every 30 seconds. You don't need any fancy mount. You do want a sturdy tripod, possibly an external power supply, and of course a computer for image processing. A few additional gadgets that I got myself. A slider. We'll see in a minute what sliders can do. So basically, while you're taking your time-lapse image, you're very slowly moving your cameras sideways. Commercial sliders, they usually sell for $1,000 and up. You can, for under $200, build your own. Here's my own attempt made from Unistrut, and yes, those are skateboard wheels. This was in the Badlands. Another gadget I am frequently using is a motorized panning heads. It offers multiple panning speeds down to 15 degrees per hour, which if you're into astrophotography, you know, this is the speed at which stars move across the sky. And sometimes I like to illuminate the foreground. So I have this battery operated dimmable video light. It runs on batteries, but if you use it at the lowest settings, which is really all you need, it runs for hours and hours. I think the longest I've operated it was for 8-9 hours, and the batteries were by no means dead. So let's take a look at one example. This is a reconstructed sod house at Toadstool Geologic Park in northwestern Nebraska. So let me play this. And this camera was on a slider. You see how it was moving through the fence. Actually, on the sod house, you see the shadow of the camera moving. And here is the same scene with a second camera. So you see my first camera moving on the slider, and that second camera was mounted on the panning head. There were some photographers in the park with their flashlights. That's what you sometimes see in the background. How is that video playing? Is that playing okay?
It looks gorgeous.
All right, thank you. Okay, here's another example. This was 2 years ago at Goblin Valley, Utah. And again, I used my video light to illuminate some of the hoodoo rock formations in the foreground. And I used my motorized panning head. And you see on that night, there was quite a bit of airplane traffic. And also, again, you notice air glow. See that greenish color, sometimes also reddish. That is fluorescence or phosphorescence in the upper atmosphere. Let's play this one more time.
So those flashes of light going across the sky, those are airplanes?
Those are airplanes, yes. A lot of people think those are meteors or shooting stars, but meteors, they are so brief, okay? They usually light up for a second or even a split second, that they're only visible on a single frame. Right? And you would barely notice them when you play back the time lapse at 15 or 30 frames per second.
And we did have one question come in from Stephen. He wants to know the effect of thousands of low Earth orbiting communication satellites. Do you see that affect your work?
That is a good question. To be honest, I haven't had a chance to do time-lapse imaging from a dark sky site, but this June I'm planning a road trip with my family back to Utah, and I think after that trip I'll be able to tell you more.
And then he had a follow-up of, do you think it should be regulated, all those satellites that are being thrown up there?
Definitely, yes. The question is, of course, who has the power to regulate things? Okay, so let's now talk a little bit about assembling those hundreds or thousands of images into a movie. So let's assume we shoot 2 frames per minute. Okay, so usually I do a 25-second exposure time, and it takes 5 seconds to copy the image on the SD card or whatever the camera uses. So 30 seconds per image, that means 2 images or 2 frames per minute. So if you, let's say, shoot for 2 hours, you end up with 240 pictures. Now, a standard video playback speed is 30 frames per second. And so if you do that, you end up with a video of 240 pictures divided by 30 pictures per second, and that's only 8 seconds. Not very long. So how do you make a longer movie? Well, one option is to take more pictures. After all, a full night can be anywhere from 5 to 11 or 12 hours, probably a bit more in the winter, depending on your latitude. But of course, that means you probably need to bring spare batteries, and hopefully your memory card has enough capacity. I like to shoot those images in RAW format, and that means each picture uses about 25 megabytes. So if you take 1,000 pictures in a night, you end up with 25 gigabytes of data. You could shorten your exposure, and you might be able to get away with that by increasing the ISO of your camera. The problem is, the higher the ISO setting, the more noise you get in your picture. So very soon you run into the limits of what your camera can do. Another option is to reduce the playback speed to 10 or 15 frames per second. That, of course, goes at the expense of motion smoothness. One trick that I sometimes apply is to dissolve or blend over one frame into the next. And then even at 15 frames per second, you still get a nice smooth playback. One trick I sometimes use is I create artificial star trails in comet mode. So there are different programs that can do that. For example, I've used a program called Star Stacks. And let me show you this example. This is again from Utah 2 years ago. This is Gorovna Arch in the Escalante National Monument. So the light you see here, that's moonlight, that's not sunlight. And this is a view towards the north. You see how the sky rotates about the northern celestial pole. In fact, the star right here, just above the tree, that is Polaris, the North Star. And those comet tail-like appearances of the stars, that was digitally created. Here's the double cluster in Perseus. That was the W of Cassiopeia. Up here, that, by the way, I think that's the Andromeda Galaxy, M31. And over here, we have the Pleiades, the Seven Sisters. Okay, so I have two video sequences with music. So I'm going to try and play them. And could you please let me know if you can actually hear the sound? If not, I'll have to change something in the screen sharing settings. So this was 4 years ago from Port Crescent State Park in the thumb of Michigan. And we got treated. I was out there with the Sunset Astronomical Society, my astronomy club based in Bay City, and we were treated to a pretty rare aurora phenomenon that's called Steve. It's this very narrow band of light. So see what happens.
The music is working correctly.
Excellent, thank you. All right, so the last one, and that's a bit longer, about 5 minutes, is a compilation of time-lapse sequences I took at the Devil's Tower, the Dinosaur National Monument, and from Yellowstone National Park. Here we go. My cameras on the slider. That light that you see, that again is moonlight, sunlight. And here's the same view with the camera on the slider. The advancing shadow of the moon setting on the mountain. This was the echo part section of Dinosaur National Monument. Yellowstone National Park, Grand Canyon of Yellowstone. Dinosaur National Monument. Here's the Big Dipper. All right, and that brings me to the end of my presentation. I put a few links here if you want to see some of those time-lapse sequences again. They're on my YouTube channel. I also have a Flickr channel for my more recent astrophotography. You can get some information on Milky Way Panorama at milkywaysky.com. And there is a photographic star atlas based on that second all-digital Milky Way panorama. And as far as I know, it is still available on Amazon and at other bookstores. So with that, I would like to thank the organizers very much for inviting me. And I'm happy to take questions.
We did have a question come in from Jean. I'm getting some reverb here. You guys are here too.
Yes, we are. I can ask the question here.
Okay.
We have a question from Jean. Is there any research on artificial intelligence enhanced technology for generating the intermediate frames in time lapses, like what is being applied to older movies?
To be honest, I'm not sure. It would definitely be a field where some of the more recent advances in artificial intelligence could be applied. I just haven't seen anything yet.
All right. Thank you. I don't know. We don't appear to have any other questions at the moment. But thank you very much. This has been wonderful. We do actually now have another question. Could we just see the links that you had up again?
Absolutely. Let me share my screen again. Oops, nope, not this one. Wrong click. Here we go.
Thank you.